Hey everyone, in this video we're going to go over section 6.4, which is the central limit theorem. So we're going to continue building on from the previous section with sampling distributions. So a sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. So if you remember, the previous example was we took samples of 10 words from the set of words in the lyrics of Beyonce's song Crazy in Love. So that was our population, the words in the lyrics. So if the sample statistic is the sample mean, then the distribution is the sampling distribution of sampling means. And so what this then means is that, and there's this little graphic that I hope that you can see. So we have the population mean, mu, and then we have all the samples that give us a sample mean, right? And everyone's is different. In the Beyonce's example, you all took a sample of 10 words and each of you had a different sample mean length for the words. And so, but all of those ideally approximate the population mean, the population parameter. So that's what this is saying. So the central limit theorem for sample means essentially says that if we have either a large sample size, and the rough guideline is that the sample size has to be 30 or more, or our sample comes from a normally distributed population. So if you already know a certain population is normally distributed, then the size of the sample doesn't really matter because it's going to be normally distributed. So if you have something that is size 30 or more, or comes from a population that is normally distributed, then the central limit theorem applies. And so what this says is that your sample is going to be approximately normal or normal with mean equal to mu, the population mean, and a standard deviation equal to the population standard deviation divided by the square root of the size of the sample. So properties of the sampling distribution. So these are I just rewrote this in a more specific way, like separating them. So the mean of the sample means, and with notation. So mu sub x is equal to the population mean. So mu sub x is equal to the parameter mu. The standard deviation of the sample means, so mu sub x is equal to the population standard deviation divided by the square root of the sample size. So back to in our previous example with the Beyonce lyrics, right, that means that ideally the mean of the means is going to be really close, as it should be equal to the parameter, which was, what was it, 3.59. And now for the dot plot that we did in the previous section, I didn't have a sample of size 30, right? If I had more students in that in-person class, then more than 30, we would have had more of a random distribution and a normal distribution, and our mean would have gotten way closer to the 3.59, which is the population mean, meaning remember, our population was the words in the lyrics to the song Crazy in Love. So had I had more than 30 students, then the mean of the sample means would have been ideally closer to the 3.59. So that's what this is saying. And our standard deviation, it will be the standard deviation of the population divided by the square root of whatever the size of your sample is. This is also called the standard error. Now, probability and the central limit theorem. Our z-score formula is still the same, and so is the data value minus the mean divided by the standard deviation. But when we are taking a sample, then and larger than 30 or normally distributed from the population, then we can use, instead of the mean of the population, because oftentimes we won't know it, we'll do the mean of the means and then the standard error. So that's why sometimes this is preferred to be called the standard error instead of standard deviation. That way we don't confuse it with the standard deviation of the population, and it's the standard error, which will be this formula. So that's what we want to remember. So you can find the probability that a sample mean X will fall in a given interval of the sampling distribution. This is similar to what we did in section 6.2 to transform X to a Z-score using this formula. So I wrote the formula up here instead of down there. So let's try this example. The mean IQ for the US population is 100 with a standard deviation of 15. 20 people are selected at random. Assume the data is normally distributed. So 20 people are selected at random. Find the mean of the means and the standard error. Because we're told to assume that the data is normally distributed, so the mean IQs for the US population is normally distributed. So that means that any sample that I take from there is going to be approximately normal. So therefore, based on the central limit theorem, the mean of the means is going to be the same as the population mean, which in this case is 100. So that's mu, the population mean, and the population standard deviation is 15. So this is going to be 100. Sorry there, clicked the wrong thing. So 100, and then the standard error is the standard deviation of the population divided by the square root of the size of the sample. So in this case, I'm going to have 15 divided by the square root of n. How big were our samples? Our samples were of size 20. 20 people are selected at random. And so that means that this is going to be 15 divided by the square root of 20. So when we put that on our calculator, rounding to one decimal place, we're going to get 3.4. So what I got was 3.35. So then I'm going to round that to 3.4. So that is the mean of the means and the standard error. Now part B is it asks what is the probability that the mean IQ of the sample of 20 people is greater than 110. So what is the probability that the mean IQ? So this is our X is 110. So I want to know what is the probability that if we pick any random person that their IQ is going to be greater than 110. So that's what we want to know. So there are two ways that we can do this. We can do it by looking up the table, or we can do it by using StatCrunch. And in the last videos for section 6.1 and 6.2, I showed you how to do doing it both ways. So let's review. So if I'm going to do the table lookup, that means that I need to convert this to z-score. So I need to then say the probability that z is greater than something. But if you remember when we look up the table for z-scores, and so let's go do that real quick. So how do I look up the table for z-scores? So when you're on our class homepage, go to My Lab and Mastering, and then open My Lab and Mastering. And that brings up the textbook. And so we're going to go to e-text. I should probably put them in a better place so that they're accessible to you without having to go through all these steps. So once the textbook opens up, go to the table of contents and scroll all the way to the bottom, and you'll see z-scores and t-values. So go to z-scores. By the way, z-scores is when we're doing population means. So when we're doing quantitative variables, and t-values is going to be when we're doing categorical variables. So click on that and it will bring up our table for z-scores. And so that's what we want to be able to look up. Now notice the shading. This gives us for z less than. Now for our notes, we want to look up the value when z is greater than. So this is not what the table is going to give us. So let me make a note of that. So when you look up the table, right, you have gives us the normal distribution and z. So the table is giving you the probability that z is less than something. And so how do you get the probability that z is greater than? Remember, the whole thing adds up to 1. So this is going to be 1 minus the probability that z is less than r blank. So we're going to find what that is and then subtract it. So how do we find the z-score? That's where that formula comes in. So we're going to bring this formula down here and find the z-score. So let me move part C down so we have more room. And so our z-score, let's find it, is going to be my x value, which is 110, minus the mean of the sample means. So that was part A. So the mean of the sample means, we found it to be 100, the same as the population mean. So minus 100 divided by the standard error. So the standard error is 3.4. It did say to round to 1 decimal place. So 3.4, and this is going to give us, put that in your calculator, and what do we get? I got 2.94 is my z-score. Now, just to recap here, this is our sample means, the mean of the means, and this is our standard error. So I get 2.94, so that's my z-score. So that means that now I can look up the value when z is less than 2.94. And so let's go to the tables. And this gives me negative z-score, so let's scroll over to the next page for the positive z-scores, and we're looking for 2.94. So I'm going to go to 2.9, which is over here, and then 1, 2, 3, 4. So, oh wait, no, that's 2.90, 91, 92, 93. So 94 is right here. So 0.9984. So 0.9984 is this area. So that means that the probability that x is greater than 110 is the same as the probability that z is greater than 2.94, which is equal to 1 minus the probability that z is less than 2.94, so 0.9984, which gives us 0.0016. So that will be the probability. So the probability that a randomly selected person from the 20 people in the sample has an IQ greater than 110 will be what, 0.16% when you convert that to a percentage. So not very likely, right? So that's what that's saying. Now if we do it via StatCrunch, let's go to StatCrunch. So you will come to the StatCrunch website. If you don't already have it open, click on Open StatCrunch, and then it will take you to StatCrunch. And then from here, we will go to Stat, Calculators, and we're going to go to Normal, right? Because we are assuming a normal distribution, which brings up the normal curve. And now here we can go directly to, we don't have to use the standard normal, right? So we don't have to standardize our or 110. I can just put my parameters. So I know the mean is 100. The standard deviation that I'm going to put in here is actually the standard error, which you got it to be 3.4. And then we're looking for the probability that a randomly selected person from the sample of 20 has an IQ greater than 110. And so compute, and notice that it gives us the 0.0016 that we got. So if you're doing anything like this via StatCrunch, just make sure that you do a screenshot of this and include it in your results, like if it's a quiz or a test. So then the best thing to do is, by the way, notice that the shading, there's just like a tiny bit of a red dot there. So that's where it's been shaded, which is essentially not very likely for this result to happen. But the way to copy this image will be go to Options and Copy, and it brings up another image. But notice that this one has all the information. It has the mean, the standard deviation, and the probability already in it. So then I'll just do right click or Control Alt V and copy image. And now when we go back to our notes, then we can put it in here. So I pasted it already in here. I did it by doing right click and paste as an image. And so that's how I put it in here. And so this is something you can do, like if you're doing a Google Doc, you can do what I did. Go to the options, copy, and then right click on the new image that it gives you with the data, and then just insert it into a Google Doc and then save the Google Doc as a PDF, or you can just share that Google Doc in the file submission for me. And so that automatically gives me access to that document. It shares it with me. All right, so then there is our probability 0.0016, which is the same thing that we did by hand. Part C, what is the probability that the mean IQ of the sample of 120 people is between 95 and 105? So you can do it the way that we did it here. So that means you will have to convert each of the two X values, right, the 95 and the 105, into z-scores, and then find the area in between. Or we can just go back to StatCrunch and back to this one. So we're going to change, right now we're in standard, we're going to go to in between, and that stays the same. The mean is still 100. The standard error is 3.4. So make sure that here when it says standard deviation that you're using the standard error. And then we want the probability between 95 and, what was the other one? 105, and compute. And so notice how it shades. So this is the probability that a randomly selected person from the sample of 20 is going to have an IQ between 95 and 105. And so same thing, I can go to options, copy. Notice how it gives me a new image to right click and copy. So I'm going to right click and copy, and then going back to our notes, I'm going to right click and I'm going to paste it as a picture. And so there it is. Pretty cool, huh? All right, so our second example. So we have an education finance corporation claims that the average credit card debts carried by undergraduates are normally distributed with a mean of $3,173 and a standard deviation of 1120. What is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance less than $2,700? So we want to find that probability, and that's part A. And then part B says you randomly select 25 undergraduates who are credit card holders. What is the probability that their mean credit card balance is less than $2,700? So what is the difference between these two questions? Right, part A and then part B. Now, notice here, part A, what is the probability that a randomly selected undergraduate? So we're randomly selecting an undergraduate from the population. So when I do this, I am really just asking what is the probability that a person from the population has a credit card debt that is less than $2,700, right? But this is X is in the population. This person, this undergraduate, is in the population. Whereas here, what is the probability that their mean credit card? So you select 25 undergraduates who are credit card holders. What is the probability that their mean credit card balance is less than $2,700? So here we're talking about the probability that the mean is less than $2,700. Right? So that's the difference. So here I need to find I need to use the central limit theorem. And is 25 undergraduates, so I want to make sure that I'm told is randomly distributed, or normally distributed. Yes, and it is. So because this example tells me that the data is normally distributed, then the central limit theorem applies, and so I can use that data or that fact to say that then the mean of the means is equal to 100, and then the standard error is going to be the standard deviation of the population divided by the square root of n. So in this case, what was our mean? The mean was 3173, and the standard deviation was 1120 divided by the square root of n, the square root of, so the sample here is 25. So that's going to be the difference. So when I'm doing this by hand, right, I want the probability, then I'm going to want to convert to a z-score. The z is less than something. So when I find the z-score, my z is going to be the 2700, my x value, minus the mean 3173 divided by the standard error. And the standard error, when you put it into the calculator, so 2700 minus 3173 divided by 5 is going to give us, what is this? 1120 essentially divided by 5 is 224. So that's what's going to go over here. And so that will be your z-score. And whereas here, we're just taking a undergraduate directly from the population. So when I find this z-score, the probability that, that z is less than something. So I need to find that z. So z is going to be my 2700 minus 3173, but now divided by just the standard deviation, so 1120. So this gets divided by the standard deviation, right? So this, the formula that I'm using here is x minus mu divided by sigma, because I'm coming directly from the population. Whereas here, the formula that I'm using is my x minus, so this is my x bar minus mu x bar over sigma x bar. So I guess technically here I should be more proper with my notation, and we're saying that what is the probability that a sample mean is less than 2700. So that's what we're finding. And so you can then, whatever the z-scores are, you can look them up in the table like we did, or we can go to StatCrunch and put them into the StatCrunch calculator. So I'm going to go back to standard, and we're going to put in our mean here is 3173, and for part A, the standard deviation is 1120. So we're going to put 1120, and we want now the probability that x is less than 2700, and compute. And so that gives us our probability. So if you're looking up the tables, you should have gotten a z-score, and then by looking it up in the book, you will get the same thing. So 0.3364. So let's call it 0.3364. So that will be this one. So the probability that x is less than 2700 is 0.3364, rounding to 4 decimal places, or approximately 33.64%. So if a random undergraduate is selected, the probability that their credit card debt is less than 2700 is 33.64. Versus if 25 undergraduates are selected, the probability that their collective credit card balance, the average balance is 2700, is going to be, so let's find that one. So the probability that the mean of those 25 undergraduates is less than 2700 is going to be, so let's go back to StatCrunch, and what's going to change? The mean is the same, but now instead of standard deviation, we're going to put in the standard error, which we had gotten it to be 224, because now we're looking at samples of 25, and we're still looking at a balance of 2700. Compute. And now that's 0.01736. And so that's what we would put as our probability. So 0.01736, is that what it was? Which we went around to 4 decimal places, so this will be 0.017123 4. And approximating it to a percent, it will be 1.74%. Right? Just move the decimal place over 2 decimal places. So that will be our probability. So the probability that the mean of the 25 students is less than 2,700 is only 1.74% versus, right, the probability that I randomly selected undergraduate, and then that probability is 33%. So this kind of gives you an idea how when you're just picking directly from the population versus when you're doing from samples of the population. And so that's how the central limit theorem comes into play in finding probabilities. Contact me if you have any questions.